Have you ever stopped to think about that invisible force that makes a compass point north or sticks a magnet to your fridge? It's literally all around us, powering our world in ways we don't even see. Well, today, we're going to pull back the curtain and really break down the science of magnetism.
Okay, so here's our game plan. First up, we're going to tackle the big one. What even is a magnetic field? Then we'll zoom way out and look at how our entire planet acts like one giant magnet. After that, we'll uncover the incredible link between electricity and magnetism, see how we can actually engineer this force, and finally, we'll dive right down to the atomic level to find out where it all comes from.
So let's start at square one. Before we can get into any of the cool stuff like electromagnets or the Earth's core, we have to answer the most fundamental question. What are we actually talking about when we say magnetic field?
Simply put, the field isn't the magnet itself, but the area of influence that surrounds it. You can think of it like an invisible force field. You can't see it, but if you bring a compass nearby, that needle will feel the force and immediately snap into line.
So how in the world do you map out a force that's completely invisible? Well, physicists got pretty clever and came up with the idea of field lines. They're totally imaginary, but they give us an amazing way to visualize the shape, the direction, and even the strength of the magnetic field.
And these lines aren't just random squiggles. They follow a very specific path. By universal agreement, we say they flow out from the North Pole and loop around back into the South Pole. But, and this is key, they don't stop there. They continue right through the magnet, making one complete unbroken loop.
Right, so we've all seen that classic image of the field lines looping around a bar magnet, but is that it? Are they always curved and spread out like that? It kind of makes you wonder, what would a perfect, totally uniform magnetic field even look like?
Well, for a field to be perfectly uniform, it has to meet three conditions. First, all the field lines have to be perfectly parallel. Second, they have to be spaced out equally. That tells you the strength is the same everywhere. And third, they all have to be pointing in the exact same direction.
Okay, so we've got the fundamentals down. Now let's scale this whole idea up. Way, way up. We're going from a little bar magnet you can hold in your hand to the biggest one in our neighborhood, planet Earth itself.
Now, here's something that trips a lot of people up. The geographic North Pole, this spot at the top of the globe, is not the same as the magnetic North Pole. And to make it even more confusing, the magnetic pole that's up north is technically a south magnetic pole. It has to be. Remember, opposites attract, and that's why the north end of your compass needle points towards it.
And we're not talking about a small difference here. Just how far apart are they? Get this, it's about 1,920 kilometers. That is a massive offset on a planetary scale. They aren't even close.
This big offset creates this really cool effect called the dip angle. Since those magnetic field lines are looping back into the Earth near the poles, a compass needle doesn't just point north, it also tries to point down into the ground. If you're at the equator, it lays perfectly flat, but if you're standing right at one of the magnetic poles, it'll point straight down. Okay, this next part is a total game changer. This discovery from the 19th century is basically the reason our modern world works. It turns out you don't have to find a magnet in the ground, you can make one. And all it takes is a little bit of moving electricity.
And it all boils down to this incredibly simple yet profound idea. The strength of the magnetic field, which we call B, is directly connected to the amount of electric current, I. It's that simple. You want a stronger magnet? You just need to push more current through the wire.
So, if we can create a magnetic field just by running a current through a wire, that means we can control it, right? Can we shape it? Can we direct it? You bet we can. And the secret is all about the shape of that wire.
And there's an incredibly easy trick to figure out the field's direction. It's called the right-hand rule. Seriously, if you take your right hand and point your thumb in the same direction the current is flowing, the way your fingers naturally curl around the wire, that's the direction of the magnetic field. Now, as you'd probably guess, the field around that wire doesn't stay strong forever. This formula just puts it in math terms. The field strength B gets weaker and weaker the farther your distance, D, from the wire. It makes perfect sense.
But this is where it gets really clever. What if we take that straight wire and bend it into a loop? All of a sudden, we're not just creating a field, we're focusing it. All the field lines inside that loop start pointing in the same direction, which concentrates all that magnetic force right in the middle.
And just like that, we now have three different knobs we can turn to dial up the magnetic power.
We can pump more current I through it. We can add more loops, N. Or we can make the radius R of the coil smaller and tighter. More current, more loops, tighter coil. They all make the magnet stronger.
Now, let's take that idea and go all out. What if we wind a wire into a long, tight cylinder with hundreds, maybe thousands of loops? We call that a solenoid. And this shape is an absolute superstar because inside that coil, it creates an incredibly powerful and almost perfectly uniform magnetic field. This is the magic behind everything from MRI machines to the starter in your car.
Okay, so let's take a step back. We've talked about what a field is, we've seen it on a global scale, and we've even figured out how to build one with a battery. But we still haven't touched on the biggest question of all. Why? Why does magnetism even exist? To answer that, we have to go subatomic.
It turns out it all comes from moving charges at the smallest possible scale. That electron orbiting a nucleus, that's basically a microscopic electric current. And what do currents do? They create magnetic fields. But wait, there's more. Electrons also have this intrinsic property called spin. You can kind of picture them spinning on their axis, and that motion creates an even stronger magnetic field. The takeaway here is absolutely mind-blowing. Every single atom is a potential nanomagnet.
Which of course raises a really good question. If every atom is a tiny magnet, why isn't my chair magnetic? Why isn't everything magnetic? And how can we take a regular, boring piece of iron and suddenly make it act like a magnet?
The answer comes down to one word: alignment. In a normal piece of iron, all those trillions of tiny atomic magnets are just a chaotic mess, pointing in random directions. They all cancel each other out, so there's no overall magnetism. But when you bring a strong external magnet close, it's like a drill sergeant yelling, "Attention!" All those atomic magnets snap into alignment, and suddenly their individual forces add up to create one big, powerful magnetic field.
And that leaves us with one last fantastic puzzle to think about. If this potential is locked inside every atom in the universe, what makes iron so special? Why does it listen to that magnetic command, but a piece of wood or plastic just doesn't care? What's happening inside their atomic structure that lets them line up on command? It's a deep question, and it really gets to the heart of the weird and wonderful rules that make our universe work.